As another neat and interesting, pretty useful in a lab setting, but not so useful in average day-to-day life device, we'll consider the cyclotron in this lesson. A cyclotron is what's called a particle accelerator, where the name is pretty much what you would guess. It's a machine that's able to accelerate charged particles from low speeds to very high speeds. Now, before we go any further, I want to ask you, how would you create a particle accelerator? How would you accelerate a charge to a high speed? The simplest way I can think of is you just stick a charged particle in a strong electric field, say the electric field between two charged parallel plates, and then just let the electric field work its magic. There might be an input for the particles, and you just let the electric field speed them up until they reach some output, and boom, you got a particle accelerator. It's not that bad of a design either. We're simplifying a lot here, but you could actually do things this way. In fact, some particle accelerator designs function very similar to this, essentially just moving the particle in a straight line through multiple voltage differences. One potential issue is you may need a long runway for particles to gain enough speed. We want particles to be going really fast, and we're balling on a budget here. So either you need a lot of space for the particle to move through, or you need a very strong electric field. But the field itself can only be so strong because otherwise you'll end up with some of the plate charge leaking off, so to speak, and we saw something like this in one of the previous modules. The electric field was so strong that charge would rather jump into the air and ionize molecules there than stick around near so much charge so close together. The alternative to using a linear electrostatic particle accelerator like this is to use our newfound knowledge of magnetism to help us accelerate our particle. But how can we do that? Didn't we already establish that the magnetic field can't increase the speed of charged particles? Yes, that's true, but the magnetic field can change a particle's direction of motion, and that's what we're going to take advantage of here. So imagine this. What if a charged particle moves through a small space of electric field, so its velocity increases just a bit, and then it somehow turns around? How do we get it to turn around? With the use of a magnetic field, of course. With the right-hand rule, V cross B, we can see that the force is initially pointing downwards, and it turns as the velocity turns. So now that it's turned around, we'll move it through another small voltage difference, but this time with the electric field reversed, because the velocity of the charge is reversed. We want to accelerate the charge, not decelerate it. So now it has an even higher velocity, so why don't we use that same magnetic field to reverse its direction again, and then push it through a reversed voltage difference again, and then reverse its direction again. If we keep doing this, just back and forth, the particle will gain greater and greater speeds while accelerating through these mini voltage jumps in between. And the magnetic field that we use, if we don't change its magnitude, it's going to swing the particle in bigger and bigger semicircles. This is essentially how a cyclotron works. Notice how the particle is not really taking up that much space either. It's just looping around in a spiral fashion, which is much easier to handle than a straight line. Now that we've got all the intuition down, we just need to show how the machine is actually structured. The trick is we've got two metal Ds here, named like that because they're each shaped like a capital D. In between the Ds, we have an alternating potential difference, so sometimes the voltage and electric field is in one direction, sometimes it's in the other, back to the original direction, and so on. This might seem kind of strange, like how does it alternate like that? But don't worry about it, we'll go over all the intricacies of alternating voltages later. We got a whole module dedicated to it, so just go along with me for now. All the while, we have a strong magnetic field perpendicular to the motion of the charged particle like this. It's easy to accomplish something like this with the use of strong electromagnets above and below the Ds. Again, we'll talk about how to create electromagnets in the next module.
I call it the nasty patty.
Now, what's going to happen if we have a source of charged particles in the middle? If we have a potential difference between the two Ds, a positively charged particle is going to feel an electric force towards the D at lower potential, which accelerates it. Once inside the conducting D, the electric field is gone, so the only force that's left is the magnetic force, which twirls the particle around until it gets back to the gap. Now this is the key. By the time it's back at the gap, the potential difference has reversed, so that the electric field points in the opposite direction. Again, the particle gains energy as it moves across this electric field and attains an even higher velocity. And this cycle continues over and over again, with the particle traveling in an outward spiral. The spiral gets bigger and bigger because the particle gains more and more energy each time it passes through the gap. Eventually, the spiral gets too big for the d, and the particle exits through some predetermined exit slit. So what's the particle's speed once it exits? Well, if it's only under the influence of a magnetic field right before it exits, we can set the magnetic force magnitude equal to the centripetal force. In other words, mv squared over r is equal to qvb. But we've already done this before. Do you remember when we were talking about the uniform magnetic field, we ended up with this exact equation. The magnitude of the magnetic force, assuming everything was at right angles, so sine theta dropped out, was equal to the centripetal force. Ultimately, we ended up with the rotational frequency of the charge, which we called the angular cyclotron frequency. Well, this is exactly the angular frequency of the charge in our cyclotron we have drawn here, assuming the electric field gap is really small. This rotational frequency is the same rotational frequency that we set our voltage to oscillate at. That's why it's associated with cyclotrons. Just doing some rearrangements of our force balance equation gives us the resultant speed v is equal to qrb over m. So if we want a higher end speed, either we need to build a cyclotron with a larger radius, or we need to increase the magnetic field strength, which would pull the particle inwards more powerfully. Now the question is, how is this actually better than our original long runway particle accelerator that just needed an electric field? Can we actually create faster particles with this new swirly particle accelerator? Well, let's see. We'll try plugging in typical values and determining the speed produced by our cyclotron, and then we'll see what kinds of parameters we would need on our linear accelerator to generate the exact same speed. To start, we'll make use of alpha particles, which are just helium nuclei, doubly charged and with a mass of 4 AMUs. For the radius of our cyclotron, why don't we just go with 1 meter? For one, it's easy to work with, but it's also pretty reasonable. It's definitely achievable in a lab setting. For the magnetic field strength, 1 Tesla is a pretty reasonable amount in a lab setting too. So plugging all this in, the final speed of our alpha particles comes out to be around 48 million meters per second, which is really fast, comparable to the speed of light actually. So a proper analysis would have to take relativistic effects into account, and the resulting speed would be lower in reality. But just for fun, let's run along with it and see what kinds of parameters we would need with our linear electrostatic particle accelerator to generate the same speed. We can use a simple energy argument and say the work done by the electric field is equal to the change in kinetic energy of the particle. So Q delta V is 1/2 mv squared if the particle starts from rest. Just dividing Q on both sides gives us the voltage that the particle would have to be accelerated through in order to generate such a high speed. Plugging everything in, we get about 24 million volts. That's an insane potential difference we have to accelerate through. To put that in perspective, the high voltage laboratory at Mississippi State University boasts impulse voltages up to 3 million volts, which is only an eighth of the voltage we need. And this is at a high voltage laboratory. That's literally their job. They have one job, and it's to produce high voltages. Lightning strikes generate a typical voltage around 300 million volts, so the voltage we need to accelerate our tiny alpha particles is around 1/10 of a lightning strike. Imagine the audacity. Looking back at our cyclotrons, just a basic 1 meter radius machine with 1 Tesla magnetic field strength will do the trick, and we don't have to go to such extreme measures just to accelerate our particles to high speeds.